Today on the show, we're diving into three striking advances from FAIR at Meta, Microsoft, and Orange Innovation. First, Meta's AutoformBot is turning textbooks into lean for-proof libraries at massive scale. Then we'll unpack a clever new encoder from Orange that separates meaning from position to improve language understanding. And finally, Microsoft's ObsCast shows how high-resolution weather forecasting can be learned directly from observations without relying on physical model reanalyses. Let's explore the first paper, Formalizing Mathematics at Scale. FAIR at Meta's paper, Formalizing Mathematics at Scale, presents AutoformBot, a multi-agent Lean-4 formalization system that coordinates frontier LLMs through Git work trees, pull request style review, dependency-aware task DAGs, and a post-merge evaluation harness that checks for, axioms, faithfulness, and proof integrity via declaration dependency graphs. Using Cloud Opus 4.6 as the main model, the system auto-formalized 26 open access textbooks across analysis, algebra, topology, combinatorics, probability, geometry, number theory, PDEs, and theoretical computer science, producing Atlas, more than 45,000 verified lean, 4 declarations, and about 500,000 lines of code. The corpus is 71.3% complete overall, with high coverage books such as reanalyses at 175 over 177 targets and complex variables at 37 over 38, while harder areas like Lie groups and Boolean functions remained around 40% coverage. Ablations on Richard Stanley's algebraic combinatorics show the full pipeline reaches 77% of targets within a 600M token budget. Removing the orchestrator plateaus at 64%, removing the supervisor drops to 51%, and removing the trace analyzer to 57%, demonstrating that long horizon planning, target level verification, and failure memory are all necessary at scale. The authors argue that the main bottlenecks are not just theorem proving, but coordination, context degradation, and adversarial verification circumvention. Let's explore the second paper, Give It Space, Explicit Disentangling of Positional and Semantic Representations in Encoders. In Give It Space, explicit disentangling of positional and semantic representations in encoders, Pierre-Antoine Lequeux, Camille Barboul from Orange Innovation, and Benjamin Pivowarski at Sorbonne University and CNRS propose a transformer encoder that separates token content into 3 streams: semantic, absolute positional, and relative positional information. Built on NeoBERT and trained on 22 billion fine web tokens with masked language modeling, the key change is that the MLM head predicts only from the semantic stream, leaving the absolute position stream free of prediction pressure. Mechanistically, this reveals that learned absolute positions collapse into a low-dimensional, 2-dimensional, low-frequency manifold capturing document structure, with 94.1% of variance in the first 2 principal components, while attention heads specialize into structure-oriented and semantic-oriented groups. Relative position bias supports semantic retrieval, but does not become a standalone positional representation. Standard encoders with ROP, or relative bias, weakly retain macroscopic structure, and entangled learned absolute embeddings lose it in later layers. On probing, the disentangled model matches or exceeds baselines on GLUE, MTEB, and SQUAD, and improves 49 of 65 Flash-Holmes linguistic phenomena, especially syntax, semantics, and discourse, showing that explicitly preserving positional structure can yield richer token representations without harming mainstream performance. Let's explore the third paper, Skillful High-Resolution Weather Forecasting Independent of Physical Models. Microsoft's ObsCast paper introduces a regional weather forecasting system that is explicitly independent of numerical weather prediction from training through inference, a notable shift from prior machine learning weather models that still depend on NWP reanalyses. ObsCast is a 2-stage architecture. An ObsCast analysis model reconstructs 0.05 degrees gridded near-surface fields from sparse surface stations plus satellite and radar inputs, and an ObsCast forecast model then learns autoregressive evolution from those learned analyses using only raw observations, with no NWP-derived labels. Over CONUS, the analysis component reduces station RMSE versus NOAA's RTMA by 11.2% to 34.5% on training stations and 2.9% to 31.5% on held-out stations for 2MS, temperature, dew point temperature, 10M wind speed, and specific humidity. while precipitation threat scores improved by 11.1% to 25% over MRMS. In forecasting, ObsCast beats HRRR, ECMWF, IFS, HRES, and NOAA GFS on most near-surface variables across 18-hour lead times. With especially strong gains for moisture and wind, it also produces significantly better precipitation skill during the first 4 to 8 hours, extending beyond classic nowcasting windows. The same pipeline transfers to Europe with Meteosat and Opera data, again outperforming HRES and GFS and generalizing to held-out stations. The model combines vision transformers, SWIN transformers, and adaptive Fourier neural operators, showing that high-resolution, operationally relevant weather prediction can be learned directly from heterogeneous observations rather than inherited from physical model reanalyses. That's a wrap on today's AI paper highlights. Thanks for watching.